One of the most important functions of current in an electric circuit is to transfer energy from a source, a battery or a generator, to an electrical device, like a cell phone. Note that the positive terminal of the battery is connected by a wire to the terminal labeled A on the device. Likewise, the negative terminal of the battery is connected to the B terminal. Thus, the battery maintains a constant potential difference between the terminals A and B, with A being at the higher potential. When an amount of positive charge, delta Q, moves from the higher potential to the lower potential, its electric potential energy decreases. This decrease, delta E, as we learned in section 19.4, is equal to delta Q times V, where V is the amount by which the electric potential at A exceeds that by B, or, in other words, the voltage between the 2 points. Since the change in energy per unit time is the power, P, the electric power associated with this change in energy is delta E divided by delta T. This is equal to delta Q times V divided by delta T, or, rearranging, delta Q divided by delta T times V. Since delta Q delta T is equal to the current I, we have P equals I times V. When electric charge flows from point A to point B in a circuit, leading to a current I, and the voltage between the points is V, the electric power associated with this current and voltage is P equals I times V. The SI unit of power is the watt, which we see from the equation is the product of an ampere and volt. As a quick example, suppose the current is 3.5 amps and the battery voltage is 5.0 volts. What is the power delivered to the resistor? We start with the power, P, equal to I times V, which equals 3.5 amps times 5.0 volts, which equals 17.5 watts. When the charge moves through the device, the charge loses electric potential energy. The principle of conservation of energy tells us that the decrease in potential energy must be accompanied by a transfer of energy to some other form or forms. In a cell phone, for example, the energy transferred appears as light energy, coming from the display screen, sound energy, emanating from the speaker, thermal energy, due to heating of the internal circuitry, and so on. The charge in a circuit can also gain electrical energy. For example, when charge moves through the battery, the charge goes from a lower to a higher potential, just the opposite of what happens in the electrical device. In this case, the charge gains electric potential energy. Consistent with the conservation of energy, this increase in potential energy must come from somewhere. In this case, it comes from the chemical energy stored in the battery. Thus, the charge regains the energy it lost to the device at the expense of the chemical energy of the battery. Many electrical devices are essentially resistors that become hot when provided with sufficient electric power. Toasters, irons, space heaters, heating elements on electric stoves, and incandescent light bulbs, to name a few. In such cases, it is convenient to have additional expressions that are equivalent to the power P equals I times V, but which include the resistance R explicitly. We can obtain two such equations by applying Ohm's law, V equals I times R. We start by substituting V equals IR into P equals IV to get P equals I squared R, which allows us to calculate the power dissipated by a resistor if we know the current running through it. We could instead substitute I equals V divided by R, again just Ohm's law, to get P equals V squared divided by R, which allows us to calculate the power dissipated by a resistor if we know the voltage across it. We now have three expressions for the power: P equals I times V, P equals I squared R, and P equals V squared divided by R. In summary, when electric charge flows from point A to point B in a circuit, leading to a current I, and the voltage between the points is V, the electric power associated with this current and voltage is P equals I times V. We have two additional expressions for the power that explicitly contain the resistance: P equals I squared R and P equals V squared divided by R. Finally, the SI unit of power is the watt, which we can see from the equation P equals I times V is the product of an ampere and a volt.